We use convolutional neural networks mostly for image processing. Therefore, we first take a look at brief image processing, and then we will see how we can basically learn visual features. And we will review the convolution operation. Then we will revisit the learning of visual features, and then we will see how we can create a convolutional neural network, and then we will see, different from last week's lecture, how we can display the architecture of a CNN. So how we use a convolutional neural network? Basically, we have an image, then we create some layers, basically convolutional layers and pooling layers, and then we make a decision if we will be doing, for example, the classification operation. Let's say we have the image of a dog, then we create some layers, and at the end of all these layers that we call the architecture of the network, we make a decision. If, for example, we will decide whether we have a dog, cat, lion, or a bird on this image, that problem is called classification. We can solve other problems. Basically, we can solve image segmentation problem, semantic segmentation problem, or localization problem, object identification and localization problem with convolutional neural networks. So everything starts with the definition of an image. An image is basically a 2D array that's composed of binary values that are called pixels. Everything you see on this image are pixels, and all these values are the brightness values. If the brightness value is closer to 0, then that color is closer to black, and if it is closer to 255, then it's closer to white. And the way we represent an image is the top of the image is here at the top left corner, which is 0, 0. That's upside down of a Cartesian coordinate system, basically. And these are the columns of the image. These are the rows of the image. And the basic definition of image processing is it's the algorithms that alter an image to create a new image. That's basically the definition of image processing. We have an input image, we have an output image, then in between we do some operations, and these operations are called image processing. Such as this one, we have the original image, we have the image processing algorithm. In this case, that's a Sobel filter, that's a special filter for edge detection. And on the right side, we have the processed image. We can do various things with image processing. For example, we can do noise removal. That's a noisy image. You see noise called salt and pepper noise. We can do some filtering in order to remove that noise. We can adjust the contrast of the image automatically, as in these two cases. We can do edge detection, which is an important operation for image processing, or we can do color adjustment, where this is the original image. If we lower the contrast, we obtain something like this, and if we make the contrast higher, then we obtain an image something like this. So what we can do with convolutional neural networks, we can do classification, which means given a sheep image or an animal image, we can decide whether this is a sheep, whether that's a bird or a dog. That's called classification. If we would like to find the location of something on the image, that problem is called localization. Okay, we can do both at the same time. We can basically, for example, find the shapes on the image. That means you need to find the shapes and you need to find the location of that image's shapes. And that's called classification and localization. And if you would like to find the individual shapes on the image, that problem is called object detection. So you basically find the bounding boxes of the sheep instances. If you would like to segment an image with respect to its usages, that's called semantic segmentation. What I mean with that, for example, this is a road, and all the pixels that belongs to road share the same operation, right? Therefore, they are grouped together and they are called roads. And these are all graphs. They share the same functionality. Therefore, they are grouped together as the graphs. And these are all ships. We are not interested in individual ships. Therefore, they are all segmented as sheep. Okay, that's called semantic segmentation. And we can do instance segmentation as well with convolutional neural networks. What I mean with that, you would like to find the ships and you would like to find the exact border of each ship. That's the problem you need to solve with instance segmentation. So that's the basic difference between semantic segmentation and instance segmentation. And all these operations you can perform with convolutional neural networks. Okay, so learning visual features. We have seen some basic filters for image processing, and we can basically use these filters in order to get visual features. And this is called manual feature extraction. And the problem with manual feature extraction is things are not that easy in image processing domain. We have a lot of variances. For example, we have viewpoint variations. So these are all statues of a woman with different viewpoints. And in order to recognize all these three statues, we need features that are independent of viewpoint variation. Okay? And illumination conditions also make life really difficult for image processing. You need some features that are immune to illumination conditions. We have scale variations. That's a very big problem with image processing. These are all humans, but this one is too long, this one is too short. And if you basically define a manual feature for human detection, for example, and if you defined, for example, the minimum height of a person should be like 1 meter, then you would neglect this guy. Or if you define a feature which says, okay, the maximum height of a human should be like 2 meters, then you would neglect this guy. So there are always these scale variations within classes. We have deformation, which is a very big problem. In image processing, edge detection is a very popular method for feature extraction. But if you define features with respect to edges, and if you have deformation, such as this one, that's a cat, then your features wouldn't work. We have the problem of occlusion. You usually don't see everything that you are searching for. Let's say we are searching for a cat, and this is the head of a cat. That's actually a part of the head. That's not even the full head of the cat. So if you are behind the full body of the cat, then your features, your manually extracted features wouldn't work. So your features should be immune to occlusion as well. Then we have the problem of background clutter. Let's say you are defining some features by hand, but if your background is closer to what you are looking for, such as this one, then you would have problems with your manual features. And this is like the biggest problem in image processing, the intra-class variation. I mean, all these things are chairs, okay? That's defined by its functionality. You can sit on a chair, right? But their shape is different, their structure is different, the material they are made of is different, everything is different. So this intra-class variation is a big problem for image processing as well. So that's why you shouldn't try to manually extract features. If you were to define a chair as a human being without seeing a lot of chairs, your manually defined features wouldn't solve the problem of finding chairs, for example. Therefore, it's always a good idea to look a lot of examples and extract features from that features. And that's what deep learning does, basically. So what deep learning does is you first create some low-level features, then you combine these low-level features into mid-level features, and then you combine these mid-level features into higher-level features, and from the higher-level features, you make a prediction. That's what deep learning does. It's not always like this. For example, for face detection, you wouldn't obtain features like this. This is just an illustration, but the idea is you start with lower level features such as edges, and then you combine these lower level features into mid level features, and then you combine these mid level features into higher level features. Okay, so how we can basically feed an image to a neural network. So let's remember what was an image. That was basically an m times m that's equal to p matrix. That was an image. That's the number of rows, that's the number of columns, or vice versa. So if we would like to feed this into a neural network, what we could do is basically we could just flatten this, make this two-dimensional matrix a one-dimensional vector, right? And then feed all the data to a neural network that would solve some of our problems. But the problem is, if we do this, if, for example, we have some knowledge about something within consecutive pixels, we would lose that information. If neighboring pixels define something such as an edge, and if you flatten this image, then you would lose a lot of information. And one problem is we have a lot of parameters. If we just flatten a two-dimensional array into a one-dimensional array and feed it as it is to a neural network, you would have so many parameters, and you would lose the neighboring pixel information, what we call as the spatial information. We wouldn't preserve this if we just flatten this matrix into a one-dimensional matrix. So instead of that, what we can do basically is we can just get some patches from the image, and from that patches we can define other features that would preserve the neighboring information as well. Okay, from one image, this is one image, we can create another image from its patches which would preserve the spatial information. And all these images we newly created are called the tensors. So from one tensor you create other tensors, and from that newly created tensors you create other tensors as well, and in the end you make your prediction or you make your inference from that tensors. That's the basic idea behind deep learning. Okay, what is that this magical operation that we would use for this operation? I mean, getting some patches, and from that patches we would define new tensors. And this operation is called the convolution operation, which is a very simple operation actually, which is just based on multiplications and summations. And for the convolution operation, what we need is an input tensor, such as this one, and a filter, such as this one. And what we basically do is we just put this filter on top of this tensor, and then we multiply the elements that are on top of each other, and then we sum them up. Okay, and the value we obtain after this summation is the new value we obtain from this patch. Okay, so instead of representing these tensors, this region with all these 9 values, we will just use -8, for example, to represent this patch from now on. So this was one tensor, which is carrying some information. And once we do a convolution operation with this tensor, we refine the information that's inside this region. And this refined information will create another tensor. And we will create a lot of these tensors. And by refining our tensors, we will come up with a decision, which may be a classification or an object detection. But in the end, everything is based on the convolution operation. Okay, and if we apply a convolution operation on an image, the result is an image as well. You see, this is the input image. This is our convolution kernel. With every pixel in this image, we apply this convolution kernel, and in the end, we come up with something like this. And similarly, when we apply this filter, or if we convolve this image with this filter, we obtain something like this. And this is yet another illustration. We just multiply this value with this value, plus multiplication of this value with this value with this value, and it goes on like this. And in the end, we basically sum them up to come up with a single value. From 9 values, we basically obtain 1 value. That's the basic idea behind convolution. So why do we need basically convolution? Why we cannot just manually define our features? Assume that we would like to solve this problem. That we would like to say something, this shape is an X shape or not. Okay, that's the problem we would like to solve. So this is definitely an X shape, because it has this axis and this axis. There is no problem with that. But this is an X shape as well. And we need to define some features that can tell this is an X shape as well as this is an X shape. And this is where the convolution operation basically comes in to hand. Assume that we have some operation that can basically find we have these features on the image. So these diagonal brightness values. We have these things on the image. And let's say we have some operation that says we have this structure on the image, and we have another operation which may say this structure exists on the image as well. So if we can find either 3 of all these operators, or 1 of them or 2 of them, then we could say the shape we are interested in is an X shape. Okay. Now let's look at this deformed or skewed X. You see, we have the same thing here and here. So if we can find this structure on the proper X, we can find the structure on this improper X as well. So we have this structure on the proper X, and we have this structure on this skewed X. So we are not just looking at the exact shape of the X. We are not defining very hard features. We are not even defining features, actually. We were just going to ask our neural network to find that features, and the neural network will be looking for features that can define the X shape. And these are the features a neural network would come up with. So we have this feature on the left side. We have the same feature on the right side as well. So we can safely say we found all these 3 structures on the right side as well. So this is an X shape as well. And the way we can find these features is the convolution operation. If we convolve the image with something like this, as in this one, for example, this is the filter to find this structure. If you convolve the image, if you convolve this image with this filter, this part of the image will be giving a high value. Because remember the convolution operation, we multiply the brightness values and the filter, and since these are all ones, if we have high brightness values here, we will obtain a high value if we come up with a structure like this. Okay, if we convolve this filter with this image, it's gonna give high results for this part of the image as well as this part of the image. And if we convolve the same image with this operator will give a high value if it sees a structure like this small x. Okay. Therefore, if we can get a high value with this filter, that means we have the small x as well. And when we convolve the image with this filter, this one, it's gonna give higher results or high values if it comes up a structure like this, or if it comes up a structure like this one. And in the end, our neural network can say, okay, I did convolution with these filters. I created, for example, 3 tensors, and when I look at these 3 tensors, I can basically see that I can find these structures on the image. So I can make a decision to say this shape is an X shape. So that's how basically the convolution operation or the convolutional neural networks work. It convolves the image and then it creates tensors. From the tensors it creates more tensors, and at the end it refines all the tensors in order to make a prediction. So we have basically 3 major operations with convolutional neural networks. The first one is obviously convolution, as the name of the network suggests. We have an operation to introduce nonlinearity. If you remember from the previous lectures, nonlinearity is important because we don't want a linear classifier. We have seen linear classifiers are not very good at solving problems. It can solve very basic problems, but real problems are not really that easy. And you always need some nonlinearity with your problems. And the third operation is pooling, which is basically the downsampling operation. Okay. With these 3 operations or 3 operators, we can basically define our convolutional neural networks, and then we need to train our network. So just defining a network is not enough. You can define a neural network with randomly initialized weights and biases. Remember from our previous lectures with neural networks, not just convolutional neural networks. The first thing is you define your network, and the second thing is you train your network so that you can come up with weights and biases. So for different problems, you can basically use the same network structure. So this is the same, this is a network structure. This is a convolution layer, this is a pooling layer, and this is flattening. Okay, this is kind of a very basic convolutional neural network architecture. Okay, you can use the same architecture for different problems, but in order to use the same architecture for different problems, you need to train the architecture with different input images. Okay, and when you train the same architecture with different input images, you would come up with different weights and different biases. Therefore, even the architecture of your network is same, your weights and biases would be different. So that's why we train our neural networks. It's not enough to just define a network. If you just define something, it's gonna be initialized randomly and it's not gonna solve any problem. We will be seeing that with the Ghana example. The non-initialized or non-trained network cannot do anything. The architecture is not enough. You need to train your architecture. So that's one thing you should definitely remember. So let's see what are these operations, these 3 important operations. The first one is the convolution operation. So what we do basically is we have a convolution filter and we have a tensor. And this, for example, is a 3-dimensional tensor. This is an RGB colored image. That's why we have a tree here. So the way we basically read this architecture images is you need to look at the depth. So this axis represents the depth, this represents the width of the tensor, and this axis represents the height of the tensor. That's the same here. So this is a tensor, this is the image, this is the input image, but this is yet another tensor. Okay, and this is the tensor for the convolutional layer, and it's still, this axis is depth. This used to be 3. For example, the depth of this tensor has been increased. And this axis is width, similarly this one. And this axis is still the height of this tensor. Okay, and remember, depth, width, and height of a tensor doesn't need to be the same as the one next to it. It can be different, and it is usually different. The usual idea with convolutional neural networks is you start with a small depth, then you increase the depth while you decrease the height and width of your tensors. So that's the refining operation. You are trying to find more and more high level features by increasing the depth and decreasing the width and height. So when you look at the architectural definitions of CNNs, you would usually see a triangular shape. Things get smaller and smaller usually. So that was the convolution operation for the CNNs. Then we need something to make things nonlinear, and this is the activation. And we usually use ReLU for convolutional neural networks, and we define this basically as a layer as well with the convolutional neural networks. That's a little bit different with the examples we have been doing with the artificial neural networks in the first lecture. Now we use ReLU as another layer. And then we have another operation called pooling or downsampling. So we said the idea of convolutional neural networks is making the tensors smaller and smaller in order to refine the information. Okay, in order to make tensors smaller and smaller, we somehow need to get rid of some of the information. And pooling is one of that operations that you can get rid of some information and you can basically continue your life with the value you gathered from the pooling operation. So max pooling is one of that pooling operations. The idea is you have the given tensor, okay, and this is the Keras definition of that. You define a pool size, which is basically the area we will be looking at on the image. That's a 2 by 2. So we will be looking 2 by 2 areas. And we define something called stride. This is important. Stride is very important for understanding the generative networks as well. Stride basically says how much we will be moving this area to right or down. So let's concentrate on this part. So we have a 2 by 2 pooling. Max pooling will just select the maximum value out of these 4 values. Okay, and 6 is the maximum of these 4 values. So we basically take 6, we put it here as the refined value for this 4 pixels, and then we move 2 pixels to the right. Why we move 2 pixels to the right? We could just move 1 pixel to the right because the stride is defined as 2. Okay. So please remember this. If the stride is 1, we move this 1 pixel to the right. If the stride is 2, we move this 2 pixels to the right. So now we are here. And the maximum pixel value here is 8. So we just skip all this 3, 2, 4, 7, and we just take 8. You see, we used to have 8 values here. Now we have 2 values because we refined this part of the image and we came up with something like this. Okay. Now we are done with the top part of the image. We cannot go right any further, which means I will go back as left as I can, and then I will go down 2 pixels because the stride is 2. I always move 2 pixels when the stride is 2. So just we move this pixels 2 pixels to down, and now we are here. Okay. And basically we have 3 as the maximum value here. Okay. And then we move 2 pixels to the right and we come up here, and the maximum value here is basically 4. So we get 4 to here. So out of this 4 by 4 matrix, now we have a 2 by 2 matrix. Okay, so we refined things here. That's basically the idea behind the pooling. Okay, so we have these 3 operations, how we can use them to create a convolutional neural network. We basically apply these operations sequentially. We have the input tensor. Okay. Then we usually apply a convolution operation, and then in order to make things nonlinear, we apply a ReLU, and then we reduce the dimension of this tensor to get less features and refined features from this tensor. And we keep going doing this. So we have the pooled layer, refined layer, we make another convolution operation here, we apply ReLU here, and then we make pooling, and we have our refined values. You can do this couple of times. Usually 2 or 3 times would solve your problem. And after doing that, now we have these features. Okay, we have this depth, this width, and this height. This is still a tensor, and this is still something like an image. But we would like to make a decision, for example, to say this image was a car, truck, or a van. So what you would like to do is, instead of having this type of tensor, you flatten this tensor. So you come up with a dense layer. Okay. And this is usually how we make the classification decision. You come up with a fully connected layer, and in the very end layer, you have neurons as many as the number of classes you would like to solve. Let's say you are trying to solve a problem with 10 classes. Okay. Then at the very end of your network, you need just 10 neurons. You don't need any more or any less. Okay. That's basically how you would use convolutional neural networks for classification problem or feature learning. And during the training phase, this is basically the definition phase. As I said, if you train this same architecture with different images, for example, I can train this same architecture with images of cars and bicycles, and I can make a classification for cars and bicycles. But I can use the same network architecture and train it with cats and dogs. And I can use the trained network to make a classification between cats and dogs. So always remember, the definition of the architecture is independent from the problem you will be solving. In order to solve a problem, it's not enough to define the architecture. You need to train this architecture with the images you would like to solve. If you would like to classify trucks, cars, and bicycles, you can use the same architecture. You just need to have 3 neurons here, but you need to train the whole network with the images of trucks, cars, and bicycles. Okay, that's one thing you should remember. So how we can use this information to write basically TensorFlow codes is pretty easy, actually. We will be defining a couple of lines for each of these layers. So conv2D, convolution 2D, is basically defining this part. Sorry. So this is just saying we have 32 depth or 32 tensors here in this part of the architecture. We have a convolution filter with size 3, which means it's a 3 by 3 convolution filter, and we have an activation of ReLU. So this line here you see is defining this tensor. Okay, this is convolution plus ReLU. Okay, I had a two-dimensional image with depth 1 or depth 3. Now I have a tensor with depth 32. Here this axis is 32. And I have a width and height that's different from the width and height of the image. Okay. And now I need to reduce the dimension of this tensor because we have too many variables here. You cannot use just these convolution layers. You need to reduce this, and in order to reduce information from this tensor, we will be using the max pooling operation here in order to obtain this tensor. Okay, we just will be using the max pool with stride 2, which means if you use stride 2, we are basically reducing the dimension, width and height dimension of this tensor into half. Okay, so that's why we have a smaller thing here, and this image is basically defining the architecture. We will see how we can basically use some tools like visual keras in order to display our neural network. Now we are done with these two layers, or with those two tensors. Now we will be defining this tensor. You see, this is thicker than this one. We had 32 layers here in this tensor. Now we will be defining a convolution layer which has 64 layers. So the depth of this one is 64. And we will still be using a convolution filter with size 3. So that's going to be a 3 by 3 convolution filter. And for the activation, we will be using ReLU as well. Now we have defined this part with this line. Okay. So each line is basically defining one layer. That's pretty easy to define. Now we are here. We would like to make this tensor a little bit smaller. Okay. We will be preserving the depth. We will just reduce the width, this part, and height, this part of this tensor. So we will again apply a max pooling with stride 2. We will be just basically reducing the width and height dimension of this tensor into half. Okay. Now we have defined this layer as well. Now we can make a prediction, but in order to make our prediction, we just need to flatten this tensor. And the way we do this with TensorFlow is you give a three-dimensional tensor, and once you say flatten, that's gonna give you a flattened network. And then we will be adding two more layers, which is gonna be, the first one is a dense layer with 1024 neurons, and it's gonna have the activation ReLU as well, and it's this guy. And at the very end layer, as you see, we're gonna define again a dense layer with 10 neurons because we would like to solve a classification problem with 10 classes. And the activation is different than ReLU. If you remember from previous lectures, the activation function would change depending on the problem you are solving. If you are solving a classification problem, you would use different activations. If you are in hidden layers, such as this one, you would usually use ReLU. If you are at the end, you would use softmax as the activation function. So that's basically it to define our convolutional neural network. This network is a pretty good network actually. It can solve a lot of classification problems. And as I said, it's just not enough to define this. This is just a definition of your network. You need to train this network with images, and you need to use images for the problems you are trying to solve. So let's take a look at the code again a little bit. We have done this last week, so I'm not gonna go into the details, but I will be basically showing you how to display the convolutional neural network. I'm using Jupyter Notebook. I installed TensorFlow basically with Anaconda. That's not that easy. You can follow some instructions from YouTube, but that's a painful process, trust me. So in order to use TensorFlow, we will be importing TensorFlow as TF. We will use Pandas, NumPy, Matplotlib for other stuff. We will be using the Fashion MNIST database. This is similar to the MNIST database for handwritten characters or digits. That's just images of clothes like Pradas or dresses or trousers. So we will be just loading the images. We have 60,000 images for training, and these are 28 by 28 images. It's pretty similar to the handwritten digits of MNIST. And when you take a look at how they are stored, basically the first column is the label, and the rest are the 28 by 28 pixels. And one thing you should remember with neural networks, while you are training a convolutional neural network, you cannot feed integer values. You should feed floating point values. So you need to convert your training and test images basically to floating point, such as this one. And when you basically display, for example, 101st image, you would come up with something like this. Okay. And in order to make things work, we need to scale. You can either use a rescaler from TensorFlow or scikit-learn. That's one option. If you're using an image, you can just basically divide it into 255. Then your images will be between 0 and 1. That's one way of doing that as well. You can do either. That's no problem. For this example, we will just dividing it into 255. Now let's take a look. One thing you need to do while you are using convolutional neural networks, you need to convert this to a two-dimensional tensor. So it should be width, height, depth tensor. Therefore, we need to reshape everything. Okay. When you take a look at the train shape, you will no longer see this. You will see 28 by 28 by 1. Okay. Now it's time to define our network. That's gonna be pretty similar to the one we defined on the slides. So the first definition is we define this as a sequential model. And then we start adding our convolution layer. So it's gonna be, the first layer will be a layer with depth 32. We will be using a 3 by 3 convolution filter. We will be using ReLU as the activation. And for the first layer, we always need to define the input shape. So since we are using a 28 by 28 images, we need to define this as a 28 by 28 by 1. So these are not colored images, these are grayscale images. So this is the tensor we will be using as the input. We will be coming back to this. Now let's take a look at the CNN summary. So this summary was giving us basically the input and output shapes and number of parameters in each layer. So this is the first layer we added, right? And you see this is a 26 by 26 by 32. 32 is the depth. That's where we defined. So the input was 28 by 28. Now we have a tensor 26 by 26. That's because of the convolution operation. Remember, we are using a 3 by 3 convolution operator, and each side of the convolution filter will cut the top, bottom, right, and left part of the image. So if you have a 28 by 28 image, the convolution operation will give you an image 26 by 26. So this was one thing that you need to remember. And I would like to show you how you can basically visualize this network. This is pretty important because if you are defining a neural network, it's always a good idea to visualize this. For this lecture, we will be using Visual Keras. You can just pip install Visual Keras and import it. You can use it from Google Colab as well, but I guess each time you need to use Visual Keras, you need to pip install to your environment. And if you close that environment, I assume you will need to reinstall it with pip install Visual Keras. Just give it a try. You just import the Visual Keras. You just define your neural network with all its layers, and you just say Visual Keras layered view legend true. And as you see, it's giving you a legend because you said the legend is true. And in the legend, it's using different colors for different layers. So yellow is basically defining you the convolutional layer. And remember our first layer, the depth 32 layer. This layer is basically a convolution layer. And you see there is a certain depth here. Okay. And the layers that are colored with red, they are max pooling layers. We have two max pooling layers in our network architecture. You see, one is right after our convolution layer with depth 32, and the other one is right after the second convolution operation, which is going to create a tensor with depth 64. And when you take a look at the visualization, so this depth and this depth is same. It's just this tensor, the max pooling tensor, is half width and height of the convolution 2D tensor. Okay. And after that max pooling, we defined a convolution layer basically with depth 64, which is this one. So this is a convolution 2D layer as well. And right after that, we have another max pooling layer. And when you take a look at the code, we have yet another convolution layer that's a little bit different from the slides. So we have a depth 64 convolution layer as well. And as you see, the depth is same. It's 64, 64. The width and height is not exactly the same. It's similar. And if you take a look at the width and height, you can see it used to be 5 by 5. Now it's 3 by 3 because of the convolution operation. Now after this, we have a flattening layer. You see, this is the flattening layer. You can see it from the legend. And then we define two dense layers, one with 64 neurons and one with 10 neurons. You can basically see it from this as well. So this is basically how we visualize our network. Please try to remember that. It's always a good idea to first define your network and then take a look at the summary in order to see whether everything is alright or not. And it's always a good idea right after the summary to take a visual look at your network to see whether the definition phase of your network is okay or not. So this was the network definition phase for our problem. And if you remember, we needed to do something else. We need to train this network. Okay. And in order to train this network, we need to define the optimizer, which is Adam optimizer in this case. And we need to define a loss function so that the optimizer knows what to optimize, which metric to optimize. Okay. And you do this with the compile commands. Once you define this optimizer and loss, you basically define the number of epochs you would like to have, and then you define a batch size, and then you just say, as we did on the previous models, the model that fits with the X training values and Y training values. And in the end, after this operation, you are gonna have this network architecture, but with weights and biases learned from our training images and labels. Okay, the basic idea behind training a network is you would like to find the weights and biases. You would like to find the values for these parameters. For example, for this particular network, you see we have 320 parameters for this layer. We have like 90,000 parameters that we need to learn from the training data. And the aim of this training operation is to make an optimization so that we can learn all these weights and biases from our training data. So in order to see whether we are doing good or bad with our training, you can just check the loss history. You see the loss is decreasing gradually and it's coming to a plateau, which is a good thing. And one thing I strongly suggest is you save your network after the training, because it takes some time. If you try to, for example, train this network with Google Colab, you will see it's gonna take like 1.5 or 2 hours. That's quite some time. And if you would like to reuse your network, you can basically save your network. It's gonna save all the weights and biases, and you can basically use this command, which is load model, to load the model that you created. You can also use the same command to load the models created by other people, and you're gonna do this a lot. You will usually use other people's networks, or you will combine other people's networks in order to solve some problems. So you need to be able to load other people's networks, and the way to do this is using the TensorFlow Keras model's load model. Okay, this is one thing you should remember, definitely. And once you load your model, you can use, for example, this command, the Visual Keras layered view, in order to visualize that. Or you can use the summary commands in order to take a look at what is inside that model. But before doing that, you definitely need to load the model. Okay, so that was basically it. Once you basically, let me show you how you make an inference as well for individual elements. So let's say you either trained your network or you loaded from some pre-trained network, and you would like to try your network in order to see whether it is doing good or bad for individual elements. So we have test images. Let's say we would like to use the 10th text image, or we would like to make a prediction, or we would like to make an inference. You need to convert this to a NumPy array in order to make the prediction. And the command you will be using is model.predict. But in order to use this, you need to basically use np.array. You need to use NumPy array in order to get a value. And once you make a prediction, remember we had 10 neurons at the very end of our network. And you see we have 10 probability values, which is saying the probability of this X test image being from class 0 is this one, which is almost 0. And the probability of this test image being from class 2 is this, which is pretty close to 0 as well. And if you take a look at the fourth value, our network says the probability of this 10th image being the fourth class is quite high. I'm pretty sure this is from class 4. And when you display the image, the class 4 is basically dress. And as you see, when you display the image, this image is from basically class dress. So that's how we define convolutional neural networks, how we train them, how we basically save them, how we take a look at their summary, and how we visualize our networks and how we can make individual predictions with our network.